Water. Water is the most important compound of our life, and therefore it is the most important compound of hydrogen also. It's a covalent hydride which it forms with oxygen. It's a life-saving compound, and as per Hindu mythology, we also call it Amrit. Now this water, remember, is the main constituent of the living beings. Our own body is almost 65% water, and some of the plants even are 95% water. It's a very crucial, very important compound, and we know that we call it universal solvent, because almost everything gets dissolved in water. Now, before moving to any of its other things, first let us understand its physical properties. I think everybody knows about the physical properties of water. It's a colorless, almost tasteless liquid, which is actually having a boiling point of 100 degrees Celsius or 373 Kelvin, and density of 1 gram per cc at what we say at the usual normal temperature and pressure. Another important thing about water is about its physical properties, that it's high dielectric constant. We need to understand that why we call it a universal solvent. The reason is you need to know that it's polar in nature. That's why it's able to form dipole-dipole interaction with almost everything. It is having a very high dielectric constant, because of which it is able to dissolve everything into it. Another thing is that it is having it develops hydrogen bonding. So all these properties makes it a very good, very important solvent. That's why we call it a universal solvent. Now let us understand its structure. See, we know that oxygen in the water is sp3 hybridized. It has bent shape. We know we have done in the case of bonding, because it's having two lone pairs like this. Now the bond angle in this case is 104.5, and this OH bond length is 95.7 picometer. This is what we have, the typical structure of water. Now due to this structure, what we know that oxygen, being more electronegative in nature, is always having a partial negative charge, and hydrogens are having partial positive charge. The dipole moment of this OH bond is towards this side, of this OH bond is towards this side, and that's why the net dipole moment is towards this side. So this is the net dipole moment we have, or the resultant dipole moment we can write as towards this side. That makes it a polar molecular species. Now, we need to know, when we are discussing the structure of water, we need to know the structure of ice also. Why we structure of ice? Why we segregate this water and ice is, the reason is because what happens is that the normal water molecule, which develops hydrogen bonding only from these two sides, because of these lone pairs, also develops hydrogen bonding with what? Like this one, with some other water molecule, and this one of some other water molecule. And now what happens is, in solid state, it requires a perfect tetrahedral structure like this. So it requires a perfect tetrahedral structure. It forms four hydrogen bonding from four sides. It forms hydrogen bonding. As a result, it requires a perfect tetrahedral structure. Its bond angle gets increased, so therefore volume increases and density therefore decreases. That is why ice floats on water, in water. The reason is because the density becomes lesser than the water, because it requires a perfect tetrahedral structure. The X-ray shows that each two oxygen atom in water molecule in the form of ice are having a distance of 276 picometer. 276 picometer clearly shows that if we are having one OH bond, we know that of approximately 95.7 picometer, we can take it 96. So 2 OH bonds makes it like it is much more than normal one. If we even subtract this, what we get is that's the length of the OH hydrogen bonding we get in this case. So this is what we have the structure of ice or the solid form of water. Now let us see the chemical properties of water. The first in the list is there, it's amphoteric nature. When this water is reacted with ammonia, remember it forms NH4 plus and releases OH minus. Whereas the same water molecule when reacted with H2S forms H3O plus and HS minus. So here it is forming a base, it is forming an acid. So that's how we can show that it is having an amphoteric behavior. We also know it shows what self-ionization. Like one water molecule combines with another water molecule and forms what H3O plus and OH minus. We have done in the case of, you will be doing later on, or you have done in the case of equilibrium chapter, that this is called what ionic product of water, and that we already know is having a value of 10 to the power minus 14. So this is how we explain its amphoteric behavior. Now let us see the second property, which is the redox reactions. When reacted with reactive metals like sodium, it forms the corresponding hydroxides and releases hydrogen. You can see here it is oxidizing sodium from 0 to +1 oxidation state, and itself gets what reduced hydrogen from +1, it gets reduced to 0. So what is happening, we can easily make out this, we can make it half, then it's balanced. So it's undergoing a redox reaction. Similarly, with very reactive non-metals like fluorine, it also shows redox reaction like this here. Fluorine, when reacted with water, gets changed to fluoride, releases oxygen, hydrogen gets what? This is how. So what is happening is this gets reduced and oxygen from -2 gets oxidized to O2. So this is how we can easily make out this hydrogen as 4. We can make it out 2. So how, and we have oxygen like this one. So we need to know this. We have to balance this by making it 4, and this can be 2. So this is how we can make out that with reactive metals, with reactive non-metals, it shows redox reactions. It's one of the most important redox reaction is its photosynthesis reaction. We know water combines with carbon dioxide and produces C6H12O6 plus oxygen. So that's the reaction which takes place between this C612. So what we get is 6 oxygen, and this is how what is happening is that the water is undergoing gas redox reaction to form oxygen also. Now let us see the next property of water is, which is the hydrolysis reactions. The addition of water to any molecule, we call it hydrolysis, because that results in the formation of the hydroxide. Now let us take P4O10, which is phosphorus tetroxide. We call it P2O5's dimer form. Now what happens is when it undergoes hydrolysis, it results in the formation of phosphoric acid. Similarly, we can have this hydrolysis of silicon tetrachloride, which on hydrolysis forms SiO2 silica or silicon dioxide and HCl. Whereas the same nitride, any metal nitride like lithium nitride, magnesium nitride or aluminium nitride, on hydrolysis forms ammonia and corresponding hydroxide. The other fourth reaction is hydrate formation. Hydrate, in this, water becomes the part of the compound, maybe hydrogen bonded or maybe as existing along with it in the crystalline structure. Like we have this one, it forms complexes, like we have hexaqua titanium ion, and this it becomes one of the ligand attached to the titanium, which we'll be doing later on in class 12th in the coordination chapter. Now, like in this case, you may be knowing that barium chloride 2H2O. Now, in this case, water is existing as water of crystallization. or it can be formed, it can be existing like we have along with copper, again as a ligand, which we usually write this compound as copper sulfate as 5H2O. The 1H2O is actually is water of crystallization in this case. So these are the chemical properties of water we have.